like to talk to you today about microprocessors and reliability. When we're thinking about reliability for a microprocessor, we need to consider three things. We need to measure, we need to mitigate, and we need to modify. So what I mean by that is for any phenomenon that concerns us, the first thing we need to do is measure it. We need to know how important this problem is, both at a device level, but also at a core level, and finally at a product level. When we've measured a phenomenon, we can then work to mitigate it. So we can design circuits that tolerate the phenomenon, design things that work around them, design algorithms, and so on. And the last thing that we do is modify. And what I mean by that is build adaptive circuits, so something that's able to measure when a problem has happened and then respond. So a simple example of this would be for soft errors. So these are particle strikes, for example, that take a silicon chip like this one, they hit a memory location somewhere and they corrupt it. So the first thing, measurement, we need to measure how often this happens under different circumstances with different neutrons or alpha particles or so on. Once we've measured it, we can then mitigate it. We can design an error detection circuit that flags, for example, a parity error that flags when an error has happened. And lastly, we can build a modification circuit, an error correction circuit, which when the error happens, corrects it. But error correction is not the only way of mitigating a soft error or of modifying behavior. We can also build a processor that when an error is flagged, restarts a computation from the beginning. So there's more than one way to solve a particular problem. This means that we need to look at microprocessors and reliability as a holistic approach. So we need to start from the device level, we need to work up through the core level, then we can go to the SoC level, and finally, system and product level. By doing this, it gives us an idea of where the effects happen and where they will be best dealt with. As an example, we can consider workload dependence. If I have 3 chips here, one of them spends all its time doing video programming, another one spends its time doing numerical computation, and the third one spends most of its time idling. We've actually demonstrated that those will age differently. So this was some joint work between ARM and Stanford that was published at IRPS recently. So what we see because of this workload dependence is that we cannot pre-assign the effects of aging. We need to look at them as a function of workload. And that means that the software and the application is just as important as the hardware and the core architecture. Similarly, when we look at electromigration, we find that the amount of electromigration is very much determined by the current swings on a few key cells. So by designing those standard cells in a reliable way, we can ensure that the behavior of a processor, including those cells, will be reliable. And so on, across the spectrum. So when we look at effects that concern us right now, for example, we're very concerned with device-level reliability for phenomena like bias temperature instability and hot carrier injection. And we're concerned about how these affect new devices, such as FinFETs or future devices, gate-all-around, and so on. In addition to that, we're also very concerned with the architectural vulnerability factor of the processor itself. So when an error happens or when aging happens, it doesn't necessarily always affect computation. And so we need to understand that better, and we're working on basically calibrating our designs, figuring out how important this effect is, or any given reliability effect is, and being able to modify our behavior accordingly. So once again, this brings us to the 3 key factors for microprocessor reliability. We need to measure effects, we need to design circuits, software, and system that mitigate them, and finally, we ideally want to be able to modify the behavior on the fly based on an effect. So we would like to build an aging tolerant processor, for example, that as it ages, observes the fact that it's aging and modifies either its frequency or some other aspect of its behavior accordingly. So there's lots of active research in each of these areas, and it's an area that I encourage you to learn more about and through Computing Now and other resources. Thanks for your time.